To convert kilovolt-amps, abbreviated kVA, to megavolt-amps, abbreviated MVA, simply divide the kVA value by 1000. The formula is MVA equals kVA divided by 1000. For example, to convert 500 kVA to MVA, you would divide 500 kVA by 1000. The result is 0.5 MVA. It is important to understand that kVA and MVA are both units of apparent power. Apparent power represents the combination of real power, measured in kilowatts kW, and reactive power, measured in kilovolts kVA. Apparent power is equal to the product of voltage and current, which are typically provided in kilovolts kV and amps. Real power represents the useful power consumed by electrical equipment. Reactive power is used to maintain the magnetic fields in transformers, motors, and other inductive devices. Apparent power is the vector sum of real power and reactive power. Real power is the power that performs actual work. Reactive power is the power that supports the magnetic fields required for the operation of inductive loads. In alternating current circuits, the voltage and current are not always in phase. The phase difference between voltage and current is expressed as a power factor. The power factor is defined as the ratio of real power to apparent power. A power factor of 1 indicates that the voltage and current are in phase and that all the apparent power is being used as real power. A power factor less than 1 indicates that the voltage and current are out of phase and that some of the apparent power is being used as reactive power. Utilities often charge customers for reactive power consumption, as it increases the burden on the power grid. Improving the power factor can reduce energy costs and improve the efficiency of electrical systems. Power factor correction can be achieved by adding capacitors to the circuit. Capacitors supply reactive power, which reduces the amount of reactive power that needs to be supplied by the power grid. When performing kVA to MVA conversions, it is essential to maintain consistency in units. Ensure that all values are expressed in the appropriate units before applying the formula. Incorrect unit handling can lead to significant errors in the final result. In power system analysis, these conversions are frequently used for scaling power values and simplifying calculations. By converting kVA to MVA, engineers can easily work with larger power values in a more manageable format. The relationship between kVA, kilowatts, and kVAR can be visualized using the power triangle. The power triangle is a right triangle where the apparent power, in volt-amps, is the hypotenuse, the real power, in watts, is the adjacent side, and the reactive power, in volt-amps reactive, is the opposite side. The angle between the real power and the apparent power is the power factor angle. The cosine of the power factor angle is the power factor. The power factor is a measure of how effectively electrical power is being used. A power factor of 1 indicates that all of the electrical power is being used to do work. A power factor of 0 indicates that none of the electrical power is being used to do work. Most electrical loads have a power factor between 0 and 1. Electrical loads with a low power factor can cause problems for the electrical grid. Electrical loads with a low power factor draw more current than electrical loads with a high power factor. This can cause the electrical grid to become overloaded. Electrical loads with a low power factor can also cause voltage drops. Voltage drops can damage electrical equipment. Utilities often charge customers with low power factors a penalty. This is because electrical loads with a low power factor cost the utility more money to serve. There are several ways to improve the power factor of an electrical load. One way is to add capacitors to the electrical load. Capacitors store electrical energy. When the electrical load draws current, the capacitors release electrical energy. This helps to reduce the amount of current that the electrical load draws from the electrical grid. Another way to improve the power factor of an electrical load is to use a power factor correction device. Power factor correction devices are electronic devices that automatically adjust the power factor of an electrical load. Power factor correction devices can improve the power factor of an electrical load to near 1. This can save the customer money on their electricity bill. Power factor is an important consideration for electrical engineers. Electrical engineers must design electrical systems that have a high power factor. This will help to ensure that the electrical grid is not overloaded and that electrical equipment is not damaged. The formula MVA equals kVA divided by 1000 is a simple and effective way to convert between these two units of apparent power. It is crucial for understanding power system calculations and ensuring accuracy in electrical engineering applications. The use of apparent power is important in electrical systems because it takes into account both the real power, which performs work, and the reactive power, which supports the magnetic fields necessary for the operation of inductive loads. Without considering reactive power, electrical systems would be less efficient and could potentially fail. Reactive power is particularly important in systems with many inductive loads, such as motors and transformers. These devices require a magnetic field to operate, and the reactive power is what sustains that field. While reactive power does not perform useful work, it is essential for the operation of these devices. The relationship between apparent power, real power, and reactive power can be expressed mathematically using the following equation: apparent power squared equals real power squared plus reactive power squared. This equation is based on the Pythagorean theorem and shows that the apparent power is the hypotenuse of a right triangle with the real power and reactive power as the legs. The power factor is the cosine of the angle between the real power and the apparent power in this triangle. A power factor of 1 indicates that all of the apparent power is being used as real power, while a power factor of 0 indicates that all of the apparent power is being used as reactive power. In practice, most electrical systems have a power factor between 0 and 1. A low power factor can result in increased energy costs and reduced system efficiency. Therefore, it is often desirable to improve the power factor of electrical systems. This can be achieved by adding capacitors to the system. Capacitors supply reactive power, which reduces the amount of reactive power that needs to be supplied by the power grid. This improves the power factor and reduces energy cost. Converting kVA to MVA is a straightforward process that involves dividing the kVA value by 1000. This conversion is useful for scaling power values and simplifying calculations in power system analysis. Understanding the relationship between apparent power, real power, and reactive power is essential for designing and operating efficient electrical systems. By managing reactive power and improving power factor, engineers can reduce energy costs and improve the reliability of electrical systems. In addition to the formula MVA equals kVA divided by 1000, it is also important to understand the units involved in this conversion. kVA stands for kilovolt-amperes, which is the unit of apparent power equal to 1000 volt-amps. MVA stands for megavolt-amperes, which is a unit of apparent power equal to 1 million volt-amps. Therefore, 1 MVA is equal to 1000 kVA. When performing kVA to MVA conversions, it is important to ensure that the units are consistent. If the kVA value is not in kilovolt-amps, it will need to be converted to kilovolt-amps before applying the formula. For example, if the kVA value is in volt-amps, it will need to be divided by 1000 to convert it to kilovolt-amps. Similarly, if the MVA value is not in megavolt-amps, it will need to be converted to megavolt-amps before comparing it to the converted value. The kVA to MVA conversion is a fundamental concept in electrical engineering. It is essential for understanding power system calculations and ensuring accuracy in electrical engineering applications. By mastering this conversion, engineers can confidently work with power values and design efficient electrical systems. The apparent power, measured in volt-amps, is the product of the voltage and current in an alternating current circuit. It represents the total power flowing in the circuit, regardless of the phase relationship between the voltage and current. Real power, measured in watts, is the power that is actually used to perform work. It is the product of the voltage, current, and the cosine of the phase angle between them. Reactive power, measured in volt-amps, reactive, is the power that is stored in and released by reactive components such as inductors and capacitors. It is the product of the voltage, current, and the sine of the phase angle between them. The power factor is the ratio of real power to apparent power. It is a measure of how effectively electrical power is being used. A power factor of 1 indicates that all of the apparent power is being used as real power. A power factor of 0 indicates that all of the apparent power is being used as reactive power. In practice, most electrical systems have a power factor between 0 and 1. A low power factor can result in increased energy costs and reduced system efficiency. Therefore, it is often desirable to improve the power factor of electrical systems. This can be achieved by adding capacitors to the system. Capacitors supply reactive power, which reduces the amount of reactive power that needs to be supplied by the power grid. This improves the power factor and reduces energy costs. The kVA to MVA conversion is a simple but essential tool for electrical engineers. It allows them to easily scale power values and perform calculations in power system analysis. By understanding the relationship between apparent power, real power, and reactive power, engineers can design and operate efficient electrical systems that minimize energy costs and maximize reliability. Let's consider some additional examples to illustrate the kVA to MVA conversion. Firstly, suppose we have a transformer with a capacity of 2500 kVA. To convert this to MVA, we divide 2500 by 1000, resulting in 2.5 MVA. Secondly, imagine a power plant generator rated at 75,000 kVA. Converting this to MVA, we divide 75,000 by 1000, which gives us 75 MVA. Thirdly, consider a large industrial motor with a power requirement of 1250 kVA. To express this in MVA, we divide 1250 by 1000, yielding 1.25 MVA. These examples highlight how the kVA to MVA conversion is applied in various electrical engineering scenarios. It's a simple division, but it's crucial for maintaining consistency and clarity when dealing with power ratings and system analysis. Remember, accuracy in these conversions is vital for ensuring the proper selection and operation of electrical equipment. Another way to think about it is this: if you have 1001 kVA transformers, that is the same as 1 MVA. If you have 1/10 of MVA, that means it's equal to 100 kVA.